So good afternoon again, everyone. If you're in room one as well, my name is Lutfi Zuri, and I'll be your moderator for the second session in this room today. We have Mr. Anand as our speaker. Mr. Anand is a co-founder of Gramener, a data science company. He leads a team that automates insights from data and narrates this as visual data stories. He is recognized as one of India's top 10 data scientists and is a regular TEDx speaker. The title of this talk is Building Deep Learning Models on Geospatial Data to Fight Dengue. Very interesting because it's also relevant to Indonesia. This talk is a step-by-step walkthrough of how to use deep learning models to classify satellite images based on OpenStreetMap building data to create more accurate population map than is publicly available. You learn how to run the learning models on geospatial data. So if you have any question, you can ask or hop in. No need to wait. Mr. Anand will answer your question in Q&A session. So without further ado, let's give a big round of applause to Anand. Welcome. Stage is
Thanks,
yours.
Rafi. Let me dive straight in. What I'm going to be doing is, well, as the talk indicates, talk about how we can manage mosquitoes. But why bother? Well, if you did a survey of which are the most dangerous animals on our planet, the top answers are roughly in this order: sharks, followed by crocodiles, snakes, lions, then mosquitoes, and dogs. Of course, people often put in humans into this list as well. That's a fair point. It turns out that the order in reality is quite different. That mosquitoes, for example, kill over 100,000 times as many humans as sharks in any given year. Mosquitoes kill roughly close to 3/4 of a million people every year, and there's just no animal that compares even closely to how deadly it is. And the reality is that it's partly a function of the infections. You can catch dengue, you can catch chikungunya, you can catch the West Nile virus, but partly it's also the breadth. There are 84 countries affected by Zika. In total, in terms of the number of countries affected by mosquitoes, there are over 100. And roughly 40% of the human population is at risk of contracting dengue. Now, with that kind of an impact, clearly it makes sense to focus on preventive measures. And there are some very effective ones. One of them is based on the Wolbachia bacteria. Turns out that there is a bacteria named Wolbachia in most insects, and that includes some mosquitoes. Not all mosquitoes, though. In fact, very few. The mosquitoes that translate dengue, chikungunya, etc., they actually don't have the Wolbachia bacteria often. But if they do have this bacteria, then they don't transmit these viruses to people anywhere near as effectively. So, in other words, if we could get mosquitoes to be infected with Wolbachia, then the risk for humans is reduced, while the risk for the mosquito population is it's a fairly benign bacteria for mosquitoes. The way this works is if you insert the Wolbachia into a mosquito and it breeds with a non-Wolbachia mosquito, then its offsprings are all going to be Wolbachia infected mosquitoes. So what that means is that if you have a wild mosquito population and you slowly release mosquitoes with Wolbachia, over time, the entire population becomes a Wolbachia infected population, which means that humans won't catch any of these diseases. This was actually tried out in far north Queensland in Australia, and the region is effectively dengue free. These mosquitoes were released very carefully in specific locations in this area, and there were approximately 40 odd such releases. And after that, they've been tracking the result for many years. And over the last 8 years, there hasn't been pretty much a single dengue case in this area in comparison with numbers that were in the hundreds every week prior to that. So, given this kind of an impact, what does it take to get this into more regions? It turns out that it's not so simple. In fact, there are a number of operational and people related problems. Firstly, the place where you release it needs to be pretty accurate. You've got to place it within a 50 to 100-meter radius. And that's because these mosquitoes are pretty expensive. And you don't want to waste a a Wolbachia infected mosquito's cost in a region where it won't carry. It's entirely possible that the mosquito would die. It's entirely possible that it won't breed. It's entirely possible that it's not in a human region, which brings us to the second issue that we specifically want to release in the most populated regions. There are two kinds of populations that we need to factor in: mosquito population as well as human population. And it's only when both of these are high do we want to release it. Fortunately, they're highly correlated. Where there are more mosquitoes, there are more humans. And the third is that all of this has got to be done on data that's reasonably accurate. How often in third world countries do we have data that's good enough that we can rely on it to a 50 to 100-meter radius? And I'm going to be showing you an example in Uganda where the data exists, but it's potentially not accessible. If it is, it's not accurate. If it is, then it's not granular enough. This apart, it's a very resource intensive process, just figuring out where to release, and you can't get it wrong. You can't iterate on it. You've got to work with the local civic authorities. That takes a lot of planning. That takes a number of volunteers who will be trained on how exactly to release and how exactly to track over time. And this planning requires a lot of specialists. One on the GIS side to exactly figure out where the human population is, and therefore figure out whether we have an optimal planning of release across these. This was a process that was effectively taking the World Mosquito Program something like 3 months to just figure out where they need to release using a team of specialists. And that's effectively where we came in. So quickly, by way of introduction, as you just heard, I'm one of the co-founders of Gramener. And our team works with clients across the globe, including Microsoft, along with whom we were partnering with the World Mosquito Program to effectively help simplify data science for everyone. And the challenge or the problem that we were tackling specifically here was how quickly and accurately can we identify the exact release locations in any city. So what I'm going to do is talk you through the core of the problem first and how we solved it. The core problem is this: we don't really have good population data at a 50-meter radius, or well, actually 100-meter would suffice, and we don't have that. The best source of population density that we have is something called the gridded population of the world, the best global source. And this gives us, for every square kilometer of the planet, what is the total population. Now, that's reasonably good, but not dense enough for us. We effectively need 100 times that resolution. So how do we convert this data into something that's at a 100-meter radius? Well, it's a three-step process. One of the things we know is that population is very highly correlated with building density. So if, as step one, we took the world population data at a 100-kilometer square level radius, and on top of that, we overlaid two things. One, vegetation data. So let's just remove any places which are, let's say, forested, for example, because people are not going to live there. People aren't going to live in oceans or rivers by and large. And overlay that with the building footprint data, because to a reasonable extent, building footprints are an indication of the number of people. Now, this method has its issues. For example, how do we differentiate between a tall building and a short building, right? And if there's a multi-storied building, the population density is going to be higher, and otherwise it's going to be lower. So that is a second order approximation that we need to factor in. But in countries where the building density does not vary too much, which is usually also those cities where we have a serious mosquito problem, it turns out that we can, by and large, use the building footprints as a pretty good proxy for where humans and mosquitoes are. And that's the second step: get the building footprints. And the third step is to join this data, effectively applying a spatial join on the 1 kilometer level down to the 100-meter level, getting it to 100-meter square grids. What I'm going to do is talk you through how we did this for Kampala in Uganda, which is the largest and the capital of Uganda. As I'm going through this talk was originally planned to have two parts. The first part, where I would take you through how we use the gridded population data and building footprint data to create the finer population density using Python. The second part was how we go about building a deep learning model that detects these footprints if this is not available. Unfortunately, I'm not going to do the latter. We realized that the data that we were using for training was satellite imagery that was purchased, which I don't have permission to share during this talk. So I'm actually going to skip a quarter of this talk, which is focused on how we build this deep learning model in and converting it into building footprints. I'm conscious that this is something that you would have been very keen on, and it really is an exciting step. Acknowledge this is a miss from my side, and I'll make it up for you by making sure that an anonymized version of this does get published by the end of the month. And I'll share that in the groups. So let's dive into how exactly we did this for Kampala. I'm going to switch over to Jupyter. Yeah. So let's start with Kampala. It's the largest city in Uganda. And that's kind of what the satellite map looks like. On this, first, let's start by importing the libraries that we need. Now, the two packages that we primarily use are, first is GeoPandas, and the second is Raster.io. GeoPandas is effectively the pandas equivalent for geospatial data if you haven't used it. And for those of you who may not be familiar with pandas, think of it as the primary package that you would use for processing any kind of geospatial data. Raster.io is specifically helpful when dealing with raster data. Geospatial data often comes in one of two forms. The first is like what you saw on the previous slide, raster data, where you have a picture and each of these points represents a specific location on the planet. And these are often geo-encoded, meaning that the image itself knows that this particular point has a certain latitude and a certain longitude. These are often rendered as GeoTIFF files, which is an extension of the standard TIFF file format. The other is vector data, and GeoPandas have some solid capability to process vector data. One of the things that we can do that is more effective in vector data is intersect two shapes and then say how much of this shape is a part of that shape. And we'll be using a lot of that. So that's where GeoPandas comes in. And then we're going to be using Seaborn and Matplotlib to plot some of the stuff. Those aren't as critical. Let's continue. The first step, as I mentioned earlier, is to, first step. Let's start with the boundary data of Kampala. Now, where does one get the boundaries or where does one get the vector boundaries for any region? The short answer is just a search on Google would get you these data sets. They are fairly popular. One popular source is the GeoADM database, but a Google search does a pretty good job of that. So here's one link from where we got the boundary information for Uganda, and this is available as a GeoJSON file. A GeoJSON file is a JSON file with a specific geographic extension. Now, when we load this data and plot it, this is what it looks like, and you can see that the shape of the region is roughly in line with the shape of the satellite image. Now, let's dive into population data. What we want is the population for every 100 meter square grid within this, for which we start with the population data at a world level and then get it down to Kampala level and then get it down to the grid level. So where can we get world population data from? So that's available from the GPW, gridded population of the world data set, which has a population count across 2000, 2005, 2010, etc. And you can download a single GeoTIFF file, which is roughly 0.5 gigabyte. That's the file that we have. And when we load that, this instantly we are loading that using Rio, which is capable of handling raster geodata. The next step is we're going to just take that region that corresponds to Kampala. So we take the window in this that corresponds to the box for Kampala. Now we computed box from Kampala's boundaries. And when we apply this, the net result is that we have an image that shows specifically the population data for Kampala. So from the overall level, we've broken it down just to Kampala. Now, there are a few other things that we are doing here, which is that if we had just taken it to this boundary, all of the region outside of Kampala would have come in, and that will mess up our population counts. So what this is doing is using a Rio functionality called masking. We're saying, look, take the world population data set and mask it with the region's geometry and make sure that you get every single cell that is touched. So if the boundary of Kampala touches any cell, even a little bit, make sure that it's included and crop the rest of it. So if there's any cell that does not fall inside Kampala even a bit, then just remove it. And then we say, look, show me only those regions that have any kind of population data. So with this, we have the population of something that's very close to the Kampala boundary. It's a little more because if there are some people living in this tiny little corner that is outside of Kampala, then our this image will actually count those people as well. We'll get rid of that later. Now, why does this tiny little grid matter? Well, the reality is that we're actually going to be going into even tinier grids at 100-meter radius. And if one of the locations that we need to release it is going to be this grid, and we are basing that on the fact that this entire cell's boundary is going to be included, or population is going to be included, then we're going to run into accuracy problems. But the other issue is also that the center of the cell literally falls outside of Kampala. And if the algorithm says the best place to release it is there, then we'd be talking to the, I don't know, let's say the counselor of Kampala saying we want to release it. And he's going to come back and say, but that's not even in Kampala. That's a different boundary altogether. You've got to be talking to a different person. And a fair bit of effort is going to be wasted that way. So these things we've learned matter quite a bit. So now we have roughly the population of a 100-meter grid within Kampala. Let's go to the next step. We want to merge with the building footprints. Now, where do we get the building footprints from? Well, fortunately, building footprints are available from OpenStreetMap. And what we did was pulled out one of those OpenStreetMap outputs. And that's available, it's available as a TIFF file. Oh, sorry, no, before that. What we need to do is, given that this is raster data, if you want to do any kind of joins, we have to convert it into a vector. And that basically means converting it effectively into the equivalent of a data frame in which each of those shapes are regions or vectors. So we do that using the library Rio. Rio also has a command line function. You saw that we had imported Rio earlier, but you can use it as a command line API. What we do is take the same TIFF file that we saw a short while ago, and then with a specified precision, convert it into a GeoJSON file. So that effectively says, read the TIFF file, save it as a GeoJSON file. Now we can use pandas to read that file. And this is what it looks like. Each row is a region which contains a geometry. The geometry is the actual shape of that region and the value. In this case, the value is the population of that region. What does this look like from an output perspective? This is what it looks like. So we have a small little cell here, a rectangle that has a certain population. We have a long strip here that has a certain population. We have this strange shape that has a certain population. So what it's done is taken all of the data in that raster image and created shapes, saying all of these shapes have roughly equal values. And that now allows us to start doing the joins. Now, this in itself would normally have been okay, The only trouble is that there is a small quirk in the way Rio works, which is that we want the total population in each polygon. But Raster actually calculates the average in each polygon. What does that mean? So what it's saying is that there is the population of this region on average is whatever this value is, not in total. So the fact that this is red indicates that on average, the population density is high here, not that this particular cell has a high population. The fact that this particular region has a much bigger area is likely to indicate that the population will be higher here. So what we want to do is convert this by multiplying it with the area. So we do a small tweak there. What we do is get the width and height of all of the polygons and convert that into each cell's width and height and update it to multiply it with the tile width and height. The tile width is basically the number of rows. The tile height is the number of columns, the other way around. And we multiply it to get the total population. Now, with that, we have these additional columns, and the tile population now reflects the actual population rather than the population per tile. And this is what it looks like. So this region has the highest population, not population density, just the highest population. And this region, which you saw had a much higher density, because it's smaller, has a lower total population, even though it's got a higher density. But at least we now have our numbers right. What we've done so far is, one, taken the world population data, cropped it into Kampala, broken it into grids of 1 kilometer by 1 kilometer, which is how it was available, and converted it into a vector format and calculated the population. Now comes the next major step, which is breaking it from 1 kilometer tiles into 100-meter grids. How do we do that? Now here's where the building footprint data comes in. Before that, what we do is first convert each of those big tiles into smaller tiles. I'm not going to go through the entire code base, but I'm just going to very briefly walk you through it. This is a function that takes a single 1 kilometer by 1 kilometer tile. And then what we do is, for this overall boundary, break it up and calculate this with the width and the height of 1/10 of that tile. Basically, create a 100 by 100 grid and convert that into a series of polygons. Now, once we have these polygons, we then use the GeoPandas clip function to say, take the overall tiles and then clip it based on these 10 by 10, which totals to 100, breaking it up into much smaller tiles. And not just that, drop the edges. You saw those small corners that were popping outside. Let me show that image again. So, those cropped images. Okay, here we are. Yeah, you saw some small regions that are getting cropped out of that. When we break it into 100 by 100, we also want to remove these. So that again we accomplish using GeoPandas, and the net result is that we have a new region, a new shapefile in which the number of grids is much larger. The original had only 561 tiles. That was from the gridded population of the world data. Now we have much more than that, 125,000 100-meter grids, which with many of the areas cropped off, and they are also more regular and rectangular. I'll show you what this looks like in just a bit, because at the moment it doesn't have much by way of data. Next, we load the building footprints. Where do we get the building footprints? Well, Microsoft has this data, or you can use OpenStreetMap data, or there is a way of using satellite imagery to create this. Like I said, this is not something that I am able to present for this talk, but there is a link that I provided, and I'll share the link to this notebook with you, where you can effectively apply a building classification algorithm to satellite imagery, which you need, well, if not at this level, something close to this level of granularity, and be able to get this kind of a footprint data set. But luckily for us in Kampala, this data already exists. So what we're going to do is read that footprint data, make a few small transformations, and we get this building count, which gives us this kind of a building footprint. What that tells us is the exact locations of each of the buildings aggregated at a slightly higher level, plotting the centroids. So now if we have the shapes of each of the buildings and we have the population at a 100 meter by 100 meter level, what we can do is compute the number of buildings and the building area in each of these grids, and then use that to morph the population. The logic is this. Supposing there are 200 meter by 100 meter grids, the first is only 5% populated with buildings. The other is 95% populated with buildings. There must be a larger population in that grid with 95%. So if I take a 10 by 10 set of grids and see where exactly the buildings are, I can distribute the population in that big tile in proportion to the building area within each of these smaller ones. So the first thing that we do is create a geospatial join. And this function, sjoin, a spatial join, is at the heart of the bulk of the transformations that we have. We take the grid data and the footprint data, and we perform an operation based on the left join, which basically means, look, give me the data against the grids. I don't care what you have footprints for, but for my grids, I want you to take all of the footprint data and put it in. And the operation is intersects. We won't go into that. The net result is that now we have a new shapefile, and this shapefile has a few additional columns, such as building count and building area, which in this case is NaN, indicating that there is one particular grid. In fact, all of these 5 grids don't have any buildings and have 0 building area. Now that's important because obviously earlier we would have just taken the overall population and distributed it to this grid naively. But now we know that there's a whole bunch of grids that shouldn't even have any population because there are no buildings there. The net result is that earlier we had about 114,000 grids and we had about 397 footprints, which is roughly buildings. Now that's created a total of 460,000 polygons as an intersection, which we must now stitch back. The process of stitching back looks like this. We do a group by on an index column. The index column is something we created against the index. And we aggregate it, pick the first geometry, add up all the building areas, count the number of buildings, and the tile parameters, we just pick up the first tile parameter because it's going to be duplicated right across. That's at a higher level. So now what we have is the original building footprint area, which was about 55 million square meters, is now distributed among the grids, again comprising of the same 55 million square meters. But now we know exactly each row or each cell in that grid, which is 100 meters by 100 meters. What is the building area for that grid and what is the building count for that grid? And as you saw, first 5 had no buildings, neither count nor area. So now we know the area and the count of the buildings in each grid. This is what we're going to take. Okay, there's one more thing that we need to do. You remember I mentioned that some of the regions are going out, some of the grids are going outside the boundary. So we also crop that area based on the population. So if we do that, it turns out that the population actually shrinks a fair bit. The original population in that gridded area, all put together in that entire grid, was about 12.8 million. The adjusted population that fits that boundary exactly, that's about 7.5 million. So when we knock off all of this white area and this light yellow area, we get the population that fits exactly within the Kampala boundary, which we can now redistribute. So that's what the final grid looks like with the more accurate shapes. Finally, we do the distribution. What we do is we distribute based on 2 things. how many buildings are there and what's the building area. Now, why are we using both of these and why not just the area? Because to be fair, this is a somewhat imprecise thing. Meaning, do the same number of people live in a given building, or do the same number of people live per square foot? It's hard to tell. I mean, wealthier populations tend to have the same number of people in a building, whether it's 3x as large or 1x as large. But on the other hand, larger buildings are a reasonably good indication of more people living. So one principle is one person per household or one household per building. Another principle is a certain number of people per square foot. We don't know. And we've left it to others to figure out what is the right geosocial model. But for the purposes of this example, what we've taken is a simple weightage of 50%. So what we're doing is for each grid saying 50% of that tile's population, we distribute based on the building count. So if there are 10x more buildings, give it 10x more weightage. And 50% of the weight is to the area. If there is 10x more building area, give it 10x more weight. And based on that, we now have the overall population within these grids distributed. And this is what it looks like. At a 1 kilometer resolution versus a 100-meter resolution, these are the densities. It allows us to effectively say that, look, in this big blob, while we know that there's a relatively higher population density, it's not uniformly distributed. And you've got to pick these specific areas to release the mosquitoes in. So out here, if we wanted to identify, let's say, 100 release points, one naive way of doing it would be to simply pick the largest of these items, the largest of these cells, the reddest of these cells, sorting in descending order. What we did was went a bit further and clustered them geospatially, which is again something that I'm not going to cover in this talk, but then took them together and said, here is an actual recommendation of release sites. If you want the top 50 release sites, here's where you would place them. If you want the top 100 release sites, here's where you would place them. Now, what we have as a result of this is that, I'll come to what we have as a result, but the net impact is that the amount of time that it took for them to compute where exactly to release shrunk from about 3 weeks to 2 hours, which was a pretty big saving. Supposing there's a new city and they have to act quick and they want to know what to tell, let's say, the city council, then in 2 hours, they can compute a plan and take it to them and say, on your map, here are the points where we are going to release these mosquitoes. So can we plan the infrastructure and permissions around that? The second is accuracy. Earlier, they needed a team of specialists and human calculation always involved a certain amount of error. Now, it turned out that based on the post-facto accuracy measure, this automated system was roughly 70% better than the original release plan. And there is also an improved efficiency in the post-release monitoring and validation. What happens here is after we release, we need to check whether these mosquitoes have actually spread around. And we need to figure out where exactly those points are that we place monitoring stations to see if what the percentage of Wolbachia infected mosquitoes are. And the planning for that also became much more efficient because they have a starting point that they can iterate on. This last part is not yet fully automated. Now, this is something that is going to be taken globally. It's being rolled out in as many as 10 countries, including in Indonesia, in various regions. And if this proves to be successful at a large scale, and we can prove that it's an economically viable and scalable model, then there is a reasonable chance that we may have brought the vector of one of the deadliest animals in the planet under control. What can we learn from a geospatial perspective? I'd say there are 3 things that we as a team learned. The first is spatial joins and the power of spatial joins. Data from one data set, specifically building footprints, can help us refine a completely different data set, which in this particular case was the population of each of these grids. Given this, we have the ability to impact practically any kind of spatial data, improving it using a different kind of spatial data. The second was the power of at least two of the libraries that I showed you, GeoPandas and Raster. And the specific capability was in being able to automate the process end to end. There was no human intervention. Basically say, here's the city, and make sure that it has the world population data, the city's boundary file, and the city's building footprint. Given this, the exact release points are the output directly. And these two libraries were the ones that made that possible. The third is that even if you don't have that geodata, it's actually possible using satellite imagery to infer that. This is the part where I was going to talk about a deep learning model to detect building footprints.
10 more minutes, we have lots of questions.
But unfortunately, that's not something that I could talk about, but that was the third biggest learning. So which actually brings us to the end of what I was going to talk about, and I'd love to take questions on this.
Okay, that was an amazing talk. We have lots of questions. I still need to order some of them first. Okay, let's start with a simple one. Is it simpler to use other map like Mapbox to segment population?
Okay, so Mapbox is a fantastic front-end tool, and if you want to visualize any maps, it's great. If you want to do a certain amount of spatial analytics, it's great. If you want to do any kind of spatial joins and post-processing on top of that, Mapbox wouldn't be the tool we would use. As a simple rule of thumb, the approach that I use is if I need to do any calculations and create new maps, then I'd use GeoPandas. If I wanted to render the maps, I'd use Mapbox. But is it simpler to use Mapbox? Yeah, I guess. Well, no, I wouldn't even say it's simpler. It's easier to expose on the browser. So if you want an application that serves it to people, then yes.
Okay. Next question. Since it's hard to get actual, the most recent geospatial data, how do we know, measure, or geospatial analysis is still relevant?
That's a good question. The thing is, there are three problems with the geospatial data's recency and relevance. The first, like you said, is can I get it? The second is if you got it, how accurate is it, both from a timeliness perspective and an actual data perspective? The third is the granularity problem that we saw. Is it at the level that we actually need? The good part is the number of geospatial resources that we have today are growing dramatically. It's the kind of revolution that we had, say, in the early 2010s on just open data. That kind of open geospatial data is happening today, which means that while we don't have a mechanism for discovering it, if we want to improve the quality of data, then it's becoming easier. But to your specific question, how do we know or measure whether it's still relevant or not? Short answer is triangulation. Meaning, supposing I have two sources, then I don't know which is accurate. But if both the sources tend to converge and they tend to have very similar values, then I know that the error in either data set is not likely to be high. Since satellite data is a pretty rich source, what we can do is apply extrapolations like this. What we could have done was taken, for example, the overall Kampala population and compared it with the population that's given from our computations on the 100 meter by 100 meter level, as well as the 1000 meter by 1000 meter level, and see what the error is. If you have a 5% error, then, well, maybe it's not too inaccurate. It doesn't have to be building population data alone. It could be, let's say, vegetation data. And if you overlay it with vegetation data, you get a third point of triangulation and potentially a fourth based on, I don't know, heat emissions as a possibility. So the short answer is, when we have data from, let's say, satellite imagery, which luckily is a lot more accurate, a lot more available, a lot more recent, and use proxies to cross-verify or triangulate any data set that you have, you at least get a sense of the spread for the accuracy. That's how we measure the relevance these days.
Okay. Next question. How did you evaluate your estimation? How do you have the ground truth for it?
So there were, fortunately, the World Mosquito Program team has a fairly rich set of alternate data sources, both from having feet on the street as well as from purchasing it from several organizations, census organizations, organizations that track satellite data, and so on. So, as far as they were concerned, the reason why this problem even existed was because there wasn't something that was accurate enough based on a methodology that they felt was accurate. The methodology that they've proposed specifically is, take the most accurate population data source at the most granular level that's available, which is the GPW. Knock out all the vegetation data. Third, use building footprints as a proxy, not using the simple formula that I shared, but using a slightly more evolved formula to identify what the actual levels are. Verify against the ground truth, in the sense doing small censuses, counting the number of people in buildings where there is an actual release, mapping that against local census data where that data is available. Having gone through a few iterations, that's where they came up with this model, and that's how we know that it's 70% more accurate. But the reality is that the effort involved in evaluating this estimation is enormous. So it's not something that one does very regularly. It's something that you do maybe once a year at best, probably once in a few years, to see if a completely new or a better model comes in. Fortunately for us, better models are also coming in, not just because we're computing it, but a whole lot of people are working on this problem. So I suspect that in any case, models like these would become outdated pretty soon, in that raw data of a better format will become more available, which will eliminate the need for evaluating simple estimations like these.
Okay, so another question. How often does population map data need to be updated for its inequality use? What factors could change it?
A reasonably good frequency that most uh, governments use is 5 years. And that's because every 5 years, the demographics changes enough for the population data to be reevaluated, which is why there's a census every 5, sometimes 10 years, sometimes more frequently. What changes it? Migration. People move from one location to another. It adds up, and over time, regions that are underpopulated become highly populated, become developed. New constructions emerge. I mean, it's not uncommon that you'd see an area that used to be a lake be drained, become a swamp, and then building construction starts and it's reclaimed. And all of a sudden, there's a huge mosquito population in that area because the people have moved in. This can happen over a time span of a year, maybe 2 years, where it's a large apartment complex construction. This adds up, and typically 5 years is when you say our data really isn't good enough for it to be used as is.
Okay, last question, I guess. Question: in Indonesia, our government's data that is still pretty scarce and scattered all over the place. How can we start with this kind of analysis?
So there are three things I would suggest. The first is that this is not really an individual problem, it's a community problem, and is best addressed as a community. So there, I'm sure, are already groups that are active in working with the government or nudging the government to release more geospatial data. Join such a group, promote such a group. And I'm not saying start such a group, because I mean, if there is an initiative, it's best to strengthen that rather than create another one and fragment it. The way I've seen these kinds of initiatives help is, firstly, awareness. People increasingly talk about geospatial data. Second is demand. If there's a large group of people that's constantly asking for maps and trying to figure out where exactly this could be found, then the government knows that there is a demand, and the the more progressive people in the government can use this as a case to say, here's a large audience, here are some of the things that they can do, so why not release it? So first, join a group that provides this kind of discussion. And second, constantly talk about the need for and share whatever geospatial data you have between yourselves. The third is create new geospatial data where possible. So, for example, if you happen to, let's say, take postal codes and create a postal code boundary using, let's say, Voronoi tessellation, then you've created new data that didn't exist otherwise. Or you take satellite imagery data and create building footprint data. You created new data that doesn't exist otherwise. Share it in this group. So that way the group becomes a hub for such discussions. In India, I've seen a group called Data Meet that does this, which has become a driving force for opening geospatial data. And there's been a considerable amount of traction, including members of the government joining this group for participation.
All right, that was a great session. Unfortunately, we're running out of time. It was packed with great insight, not only for Uganda, India, but also relevant for Indonesia. Thank you so much for Mr. Anand Subramanian and also for all you who participated in this session. Allow me to close this session and see you soon in the next session. Let's take a short break. Bye-bye.